our perception is a much more active process. A camera just takes these individual pixels and processes that to a certain part, but a camera is not really seeing something. At most perceiving individual pixels, but it's not seeing objects in there. Right? It does not care about them, and it does not get that together. The brain does so, and it is, as I would argue, an active process that's happening there. It's not a perception just coming over you without your brain having done it.
Hi, I'm Craig Smith, and this is Eye on AI. In this episode, we sit down with Björn Ommer, a visionary in the field of AI, to discuss the advancements and implications of generative models in technology and society. Bjorn gives us a fascinating look into the inner workings of diffusion models, the importance of creating AI that operates on consumer hardware, and the significant strides made by his team's creation, Stable Diffusion. As we tackle the complexities of AI's role in the model world and the steps toward democratizing AI technology, Bjorn shares his expert views on the balance between open source innovation and proprietary development. I hope you find this conversation as captivating as I did. So why don't you start by introducing yourself, where you got your education, how you got into AI, and then we'll start talking about, obviously, Stable Diffusion and then everything that's going on.
My name is Björn Ommer. I'm holding a chair for AI at University of Munic for 2.5 years now. Beforehand, I had my professorship at University of Heidelberg. And before that, I did my postdoc in lovely Berkeley in California. I got my education, my PhD from ETH Zurich in Switzerland before that. Now, how did I get into AI? I was looking for challenges for open frontiers that are out there. And I very early on figured out that probably people have been traveling to the moon, been to the deep ocean and everywhere else on our planet. But the biggest frontier that I thought we were still having, and I love to explore open frontiers, is actually our mind, our brain, understanding things and being able to comprehend the world around it, which is like super complicated. And out of all the ways that you could think of our brains making sense of the world, it was really our eyes, vision, being the one that I found most attractive in order to study that, because of that being such a complicated sort of window out to the world, sort of capacity that we have in making sense of what arrives there at our eyes.
And was that, you're pretty young, so was that before convolutional neural nets?
That was way before deep learning, yeah. Okay. So I've seen the world beforehand, I've seen it afterwards. Yeah. And guess what? When I'm teaching classes, it's always like these days, students totally get hung up on deep learning. But I try to here or there also tell them lessons from what we had beforehand, because it's not all outdated that we did, what we did beforehand.
Yeah. And then how did you move into the Stable Diffusion project?
Yeah. So we for long done like retrieval tasks, addressed that, recognition tasks, and so on. And that has quite a bit of value to it. But eventually it comes to this point where you feel like, how are we making progress there, right? I mean, eventually you might find pixels that are correlated with class labels in your data sets, and this only goes so far. And I was wondering, isn't there another way that we could actually figure out whether we're making progress or not? Isn't there a way that I could more carefully diagnose whether the model has actually learned something about the world or not? Mm-hmm. And to that extent, generative models actually became super appealing to me, and probably also to a lot of other people in the community, because there you can turn that process around, right? You can say, like, with a discriminative model, a model that's trained on recognizing a particular object, you could say, recognize all dogs and separate them from cats. But it might be that the model actually figures out that a bone is much more indicative and easier to learn to figure out what a dog is, holding a bone in its mouth, than anything else. But if you then turn the process around and do what a generative model does, essentially say, show me what you think a dog is, and outcome only bones, then probably went the wrong direction. And that's how I in my lab get really excited about generative models. Now, it turns out that it's a challenging task being able to learn the visual world out there and being able to reproduce what we see out there just in a pixel space. We explored several different models, and you very easily sort of run in the standard dilemmas that we're having these days. You, on the one hand side, want to have like great quality, and on the other, you want to capture the world in all of its breadth and diversity that is there. And quite recently, novel model architectures came about. Transformers that people might have heard of, or even more recently, diffusion models. And these promised actually to bridge this divide, this gap that we had between the quality and the diversity. And it turns out, yeah, that is to a certain extent true. But at the same time, I saw that new issues actually arrived. These models got more and more complicated, consumed more and more compute, and needed more and more training data. So we were wondering, like, where will this eventually lead us? Aren't we moving in a direction? And that's what it seemed actually before we were working on Stable Diffusion. Aren't we moving in a direction where in the very near future, only big companies would have the computational resources, not just to train these models, but even to take the models that have been trained and apply them? And so it turned out, right? I mean, there were these visual synthesis models, and that goes beyond like to other disciplines as well, which were so big that you needed supercomputers to just run these models, not even train, but to just run these models. And I was concerned about that to a certain extent, because if you really consider this generative AI becoming what I believe it now has turned out to be, a critical technology, which becomes really the foundation. I mean, that's what we call it to a certain extent, also foundation models, a foundation for everything else, not just the research that we're here doing in our fields, but everything else where we create values essentially in our societies. And then you get sort of tied to just very few companies that can actually lay these grounding for this new technology. That comes with a lot of risks, right? I mean, on the one hand side, you could say, like, sure, we need creativity. Like, the more clever minds, the development of future technologies built on, the faster it goes, and the more diverse the outcome also would be. And that was one concern. But there are others, right? If it's a critical technology for our society, and it's eventually held in the hand, the future development is in the hands of just like a few companies that you have out there, that has actually profound implications, let alone like privacy issues and so on, if other businesses have to run their precious data to just those companies. And so we were wondering, how can we actually democratize the development of future generative AI? And it turned out for us, it's key that this technology is not just powerful, but at the same time, it's also widely accessible. And that means not just open source, which I believe is crucial for foundational models because they are this critical commodity. But third, it also means this technology needs to be really accessible to average users who don't have a supercomputer in their backyard. So that meant for us, we targeted consumer hardware, $300, $400 of a standard GPU that you could run it on. Stable Diffusion these days runs on your mobile phone even. And with that, you open it up to really a broader set of researchers and to a broader set of entrepreneurs that can use this technology now if you don't just need a supercomputer.
When you were looking at generative AI, was that after the transformer algorithm appeared or before?
So we were looking at that beforehand, but sure, the transformers changed things quite a bit. And we were working with technology before transformers, variational autoencoders. We had this paper, we called it Variational UNet, which tried to disentangle appearance from posture so that you can animate human beings, change their gait and their posture as they're walking without changing their appearance at the same time, so that you want to disentangle prior to like transformers really keep getting traction in the vision community. But then we continued and adapted our approaches as new technology really came about. And the latest was evidently then diffusion models, which led to what people now know as Stable Diffusion.
And diffusion models for listeners, can you give layman's description of what a diffusion model is?
Sure. It's actually not too complicated. So one key foundation I should mention there, and that is beforehand I mentioned discriminative AI and discriminative models. That meant you show the computer a lot of images and say like cat, 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 dog, 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 and the model actually figures that out. What we're these days doing in generative AI is mostly what we call self-supervised learning. Right. That means we show the computer just images. Now, how would the computer start to make sense if you just presented images and don't say what's there or what structure is there? For that, we utilize self-supervision. So in a nutshell, in diffusion models, you give the computer a training image. You add noise to this training image, just a tiny bit, so that you and I would not even notice the difference. But you repeat this process of adding noise hundreds or even thousands of times, so that the end result looks like you plucked the cable from your TV set. Pure noise, nothing left. You do that so that you can turn that process around. Present the computer a noisy image and say like, hey, this tiny bit of noise you can make up for, right? And sure, the computer, in that case, a neural network, an autoencoder, as we call it, can do that. Then you start with your pure noise that you have, and eventually you end up not exactly with the image that we started with a clear image, but with something which is conceptually very similar to understand, to represent, I should say, the distribution of all the images that are out there.
Then you connect it to a language model so that there's a conversational interface, a natural language interface, or...
Correct. So diffusion models itself don't need that, right? They are, as we call them, unconditional models, or they can be unconditional models that just learn the distribution of all the images, like set up a space of how images are situated with respect to another. And this is important just to stress this point there. Think of your training images as being tiny islands in the Pacific with lots of water around them. And what the diffusion model is, it learns a space so that islands which are somewhat similar get closer together. So you essentially start building bridges across the water, linking those islands together so that you can interpolate, that you can hallucinate, so to speak, what's between two islands, where so far has just been water. You can essentially recreate additional islands that haven't been there, additional landscape that hasn't been there, which kind of mixes or blends together the islands that you had in your training data there. But a user typically wants to have control and not just synthesize arbitrary images, right? And that's where textual site information or other site information comes into the game. So you take this diffusion process and say, like, as you're denoising, I tell you, it should be an image of a cat, for instance, right? And a brownish cat or whatever else. And then the model learns to incorporate this site information as well. Now, in what we were setting up there, we used the transformer architecture to incorporate the textual site information there. But it's not just that you're limited to textual information. You can also utilize images and say like, hey, create an image, but it should look somewhat similar to this other image that I provide you, and then stylize that image, for instance, right? You said like, I take a photo from you, but render it in the style of a certain artist, and then the image is changed and recreated, so to speak. This photography of yours is recreated with his other concepts in mind.
I mean, there is style transfer, but that's not generative.
We can do style transfer with generative models, and actually most of the style transfer these days is actually done with generative models, or as the public calls it, with generative AI. Because again, like, we are generating new data there, and for that we have learned in a generative manner the distribution of all the images of a particular style.
What are the challenges of making this available on, as you said, consumer hardware?
The biggest challenge is that you want to learn a model which fits on consumer hardware, has limited memory in that case. For those that are more versatile there, we aimed at something that has 10 gigabytes of memory. These days works on mobile phones with 2 gigabytes or less. But at the same time, you want to have a model that kind of captures all the visual world that is out there. And for that, you need to present it quite a few images, billions of images in our case, hundreds of terabytes. So how do you get hundreds of terabytes fit into 10 gigabytes, or even like take essentially the entire internet out there and make it fit in your mobile phone so that you can take it with you? This requires a lot of abstraction. I believe that is the core of intelligence, right? Taking lots of data and abstracting it so that you capture the essence of the reality as it's depicted in your training data.
You talked about the active nature of perception, but also differentiating, like, what does the model focus on in a scene?
Yeah.
Can you talk about that a little bit?
Yeah. So there are different takes on how perception actually works about. And psychophysics has been dealing with this for a century and more. What I find quite appealing is this understanding of the brain really constructing a model of the reality as it's presented to our eyes. And this is an old sort of take on what we have there. Hermann von Helmholtz more than 100 years ago, Gestaltists 100 years ago, were already considering that to a certain point, that our brains are actually, that perception is an act. It's not a reaction to something. It's an achievement actually for us to create to create this impression of what we're seeing there. And it's not just something that totally passively comes over us. I know that this is hard to conceive of because we are constantly seeing, and we're apparently it happens so effortless, and we see this with Escher rendings every now and then, that apparently there's more to that, and that there is actually a cognitive process going on. But on a day-to-day basis, we're not wondering about that and seeing this, apart from you being a vision researcher like myself, and then you get hung up about some of those details. When you think about like a super complicated being presented to your eyes, you have this process like, where do you actually allot your attention? What do you focus on to actually make sense? I mean, we can, most people probably don't even know this. We're not like a computer camera. We have a tiny foveal area, where we can only read letters, where we can see sharp, and the rest we don't even see. That's why we constantly are doing saccades. So we're focusing our gaze at certain parts, and the same happens with our attentive process as well. It's only that this happens so quickly in a very intriguing manner that we sort of paste all of these tiny crop outs of reality together, that we get this impression that we see everything sharp and all with the same detail at the same time. Now the question is, what of that should we carry over to the computer? Because it turns out it is a complicated problem. Like, one of the most complex problems that I find very appealing to also research on is, for instance, the binding problem. So you have millions of pixels in image, and it's not that it's just like individual grayscale or colors that you actually perceive, and they make up trees and buildings and so on, right? I mean, a building is more than just individual colors that you see there. It's structure. It's very complicated structure that has actually emerged, and that requires to bind together information from faraway spots in your scene that's presented to then assemble the structure that we actually see. In my talk, I was showing this example of a flock of birds. They are flying in a triangular shape in the sky. How do you see this triangular shape? None of the individual birds has something triangular on them. Right. It only happens when you bind the individual birds, which are individuals. I mean, they're separate. And the next day they found they're flying in opposite directions, or build a square shape in the sky, or whatever else that is. So this emerges out of this ensemble of birds that are coming together, and your brain is only able to actually see the triangular shape by binding together these faraway spots, and that requires attentive processes, pre-attentive processes, linking that together. So the question for us, and a long story short, as vision researchers, was always, how can we actually make this feasible, computationally feasible also? Because you cannot try out all combinations. Apparently the brain also is not doing that. You have rapid feed-forward processes that are able to mitigate this impression of there being a triangular structure. And with attention, we now have concepts, for instance, that go in that particular direction, but which also don't scale to arbitrary many pixels. The kicker here was, when I want to represent scenes, there's a lot of local detail, texture, colors, and so on, that you want to separate from representing this triangular shape, for instance, of the birds that I have there. The feathers that each individual bird has, you don't care like where each individual bit and piece of the feathers was pointed, right? You just care about the overall color that this bird had, like how feathery or whatever else it was, a bit of the texture, but the rest I wouldn't even notice if a single pixel is off. Now, if I were taking something like a diffusion model that we talked about beforehand, which is great in capturing these long-range interactions, the long-range context of a scene. If I were to take this model and apply it to represent the local texture, it would just get hung up on all of those local details. And it turns out that other architectures, convolutional neural networks that we had beforehand, are great perceptual compressors to abstract away all of those details. So it turned out that actually a combination of these two architectures is the best way to go about. One that compresses and captures the local detail, standard convolutional architecture, and then taking a more modern, like long-range contextual representations represented by a diffusion model and combining these two together. And then you have stable diffusion in essence.
Because when a camera sees a scene, even if at some level it's delineating objects, everything is equal.
I guess that's the fallacy. I don't consider our brain as this entire seeing apparatus together with the eyes as being a camera, right? As I said, like our perception is a much more active process. A camera just takes these individual pixels and processes that to a certain part, but a camera is not really seeing something. It's at most perceiving individual pixels, but it's not seeing objects in there. Right? It does not care about them, and it does not get that together. The brain does so, and it is, as I would argue, an active process that's happening there. It's not a perception just coming over you without your brain having done anything to that.
Right. So what you're talking about is the computer system, whether it's stable diffusion or convolutional neural nets, they're creating a representation of the scene. Mm-hmm. And then in that representation space, it's much easier to determine the focus speed.
Yeah. So when you want to be able to synthesize images, for instance, you need to eventually go through a bottleneck, have a very compact representation. Other than that, you would never be able to get these billions of images sort of summarized and be able to synthesize something new from that. And this has it that this compressed space needs to have certain regularities, ways in which you can present it a bunch of training images and it can then generalize. I guess that's the key word here, generalize to novel data that it hasn't seen in the training phase, which is somewhat off from the training data, but in a way that we would probably not even notice as human beings. And that's what you want to teach a computer, because you will always present it just a finite amount of training data, and you want it to generalize to new data. These are the island, this water between the islands, where you want to create new islands in between.
Yeah. And that mechanism is in stable diffusion, it's the attention mechanism that's used in the transformer algorithm.
So first off, I would say it's the diffusion process itself. Okay. The attention process. So diffusion models is a bit tricky. Now we're getting into detail. It's a bit tricky calling diffusion models itself a model, because it's just a diffusion process there as a training paradigm, so to speak. The question is really how you incarnate that. And for us, it was this encoder-decoder architecture, something that takes a representation, has to go through a bottleneck, so you get the compression, and then deflate it again to get in the same dimensionality as your input there. That itself goes a certain way, but now you start talking about like blends of architectures. It meant for us that we not just have this, but in addition have what's called self-attention, for instance, to put this encoder-decoder architecture, so to speak, on steroids. Then you want to have sight information like text coming in. That meant for us incorporating cross-attention, a concept by means of which you can take textual tokens, as we say, a textual representation, and as we're doing denoising, then control the denoising process happening in this encoder-decoder architecture. So you really see that it's not a one-size-fits-all approach these days, where you would say like, hey, I have a single architecture end-to-end, throw the data in and then hope for the best. But it's actually that we try to utilize the best of different worlds there and bring that together. And with that, make up for the weaknesses that one architecture has by the strength of another architecture.
You've chosen to make this open source.
So as I said before, and I considered this to be a crucial technology for our society, One thing that is foundational, and one of the limitations that we had beforehand, was predominantly that these models did not run on consumer hardware. And with that, only a few companies were limited to that. And our goal was to lay something like Linux or other open platforms that as many people as possible can utilize. And open source was evidently another crucial part in coming up or realizing this vision.
I've talked to a lot of people about open source, and that's what we started talking about, this dilemma between the concentration of compute in the private sector and how that limits other researchers or smaller companies from developing similar products. And so Meta has chosen to open source its Llama series. You guys, or you, I don't know who, have open sourced Stable Diffusion. There are still more powerful models in private proprietary models in different corporate under different corporate ownership. And one theory that I've talked to people about this open source proprietary debate. Ultimately, open source financial resources or to pay for the compute. And so the private sector is always going to be ahead and always going to have models that are productized that are superior to open source. But then there are other people that argue open source ultimately wins. So I'd like to hear what you have to say about that.
We'll see who wins, and I hope that society overall is winning. And we're developing technology. I mean, it's fun to be working on that and so on. But I guess our field has stepped into an arena where what we're creating starts to matter, starts to have implications. Now, I believe society has most benefit from that. And it turns out that our European Commission also starts to think in the same manner. You've probably heard open source models there play a special role in the regulation, are exempt from certain regulations for that very reason. We see private companies now also going in the direction of open source. We see that open sourcing things seem to be also beneficial to here or there attract VC money to create and create attention of people, which these days is fairly important factor, especially when you are a startup and want to acquire money. And we have with a French company seen that open sourcing there can help quite a bit with German companies as well, rather than doing this all under the rug, totally closed source. For many of the lab, I see open source for that reason being also attractive. Now there come other things. These models have great costs to them, computational costs, for instance. If several entities could share in the developmental cost, and with that also not just like the economic costs, but also costs like the CO2 footprint and so on. Like, why have several labs do the same thing again and again and again, and then pollute the environment with that? If we could share in that, create larger sort of utilization of the value that we have there, all of that you see more with open source models. And that's why I see that it's, I would argue, more beneficial for societies. It is also a way to create more revenue for the companies to a certain extent. And it's just a matter of time, essentially. I mean, your mode is not an infinite mode, right? It's just a question whether it's days, weeks, month, or whatever else it is. But eventually others will come to that point as well. Is that worth investing billions of dollars for a fairly short amount of time? Something that we need to ask ourselves, potentially even with partial governmental support to startups and so on. It's probably advisable to then give also something back to society. And then there are other things like risk mitigation and so on. If these models become critical for society, you want probably lots of researchers testing them, red teaming there, for instance, which becomes all harder if it's just a closed source model.
Yeah. Yeah. Do you think that governments will try and tip the scales toward open source? I mean, again, the open AI debacle, I think, woke everybody up to the danger of not having some oversight. I mean, they're all good people.
Just imagine, this is the crucial technology that in the future we will build our further platforms on. And then you're dependent on this one company. And whatever, they might even have all good intentions, but then something weird happens inside the company. And what you then do if you're a startup or a company or even a government, and you build everything that you have based on that. Like in earlier days, you used operating systems from some well-known companies, and you buy it and it works pretty much itself. Here or there, you unfortunately need patches, but you're good to go for quite a while. But these days, you would need the servers. And if tomorrow they're shut down, then essentially all your business ain't going to work anymore. So I guess that woke up quite a few people seeing after last week's developments in the European Union. And that seems that at least there is this clear talking about open source models in that case, but we'll still need to see how this eventually turns out, because that will have tremendous implications.
Yeah. So going back to the compute, governments can play a role in making compute available to a wider audience.
Like if we actually consider these models to be critical for what's going to happen in our societies there, then compute is the critical commodity to make this happen. Much like electricity, water, and so on in the past, it's in the future going to be compute of the kind that we're needing it there. And with that being foundational, governments probably should also have a play in that case. I'm very much for private and public partnerships in actually supporting that. There's a lot of small companies that would just not be able to bring up the money, let alone like the people that could actually host such infrastructure. And they would probably be happy to just buy in there and then sort of have the running costs being for the system then being taken over. So I see there a win-win situation for everybody.
Yeah, every country is going to approach it differently. I know there's a lot of talk in the U.S. about creating a cloud credit system or something to give researchers or small companies access to GPUs, and I imagine that's happening in Europe. It reminds me a little bit of how different countries have approached the internet, and there are smaller countries that have free Wi-Fi as a way of, generating economic activity. Do you think that kind of thing will happen, that some countries will form compute resources, whether it's on a credit system or even building, national server farms to supply compute to the not only private sector, but to the research community?
Progress in our field of generative AI has happened super fast over the last year. And I guess politics with that have just started to learn what it means to have this technology around, this technology being so rapidly developing. I've been advising here or there and been asked by politicians to set the stage, explain everything that's going on. And from that, I can just tell that they started to understand the necessity in that case of this technology and the commodities that we need to further develop this technology. And my understanding is that all Western countries and politicians, they're until now have finally sort of got their head around this technology is there. It's probably also going to stay. And there are certain sort of responsibilities that probably also central governments have in putting that together. But I see in the Western world, at least, striving towards that direction. Now, in the European Union, for instance, there's discussions about that. But to what extent this will be realized on a cross-European level, we'll still need to see. For me, it's like the Airbus is a great airplane company, or they have built great airplanes, but it took quite some years for them to come off the ground, right? And I doubt that we have this time in generative AI. Here in the US, the story is a little bit different. At the same time, there's also economic constraints in there. For that very reason, I was sort of opting for private-public partnerships, because companies are making revenue from this technology or these resources being there right away. constantly sort of adding new hardware to that. So maintaining, I mean, not just like electricity, but also investing in new GPUs there, but also help with just getting the startup of that these server farms that we need for that being funded. And the same I would hope also in European countries. I hope that politicians are more and more sort of seeing the responsibility that they have with that, but we also need to give them that they've just learned what generative AI is within a few months.
Things have moved so quickly. I worked for a couple of years on this National Security Commission on AI, and that's the mission, is to educate, in that case, the national security community, but more broadly, the government. There was a lot of optimism and hope in the recommendations that were being written, but the follow-through has been painfully slow. So the other flip side of that is to make models that require less compute. How do you go about doing that?
So there are different takes. One was what we've been doing with Stable Diffusion, create models which right from the bat consume less hardware and resources that we have there. And I guess that's an advisable direction, especially when you set up a new foundational model. The other side is taking models which are already existing and making them more lightweight. Standard approaches for that are distillation type of approaches. That, however, is a costly process. And we've seen a lot of startups who are now waving with, hey, we have this super fast model and so on. But this itself, in a lot of situations, can take as much resources as training a model from scratch almost. So you train a large model and then you train a small model and essentially like have tremendous sort of extra costs. What I find super appealing there is then the third stage, which is take models which are already existing, potentially even smaller models, and empower them, make them better. We are having, for instance, ongoing research there where we have published like first bits and pieces of, where we take a smallish model, which can also be an older model there, and increase its resolution. Turn a model which is just giving us low-res output images and turn that into a megapixel size image there without requiring much extra compute during inference and without any costly training stage there, by embracing more novel architectures like flow matching approaches, for instance, which turn out to be complementary to what we've been doing in diffusion models.
Yeah, can you explain?
Diffusion models, I mentioned before, and how the training goes. Now, there's a different understanding, like what's actually happened with a diffusion model. And that is that the diffusion model actually describes a trajectory through image space. I was talking about these islands in the Pacific. Now, there's been recent developments, flow matching, for instance, optimal transport approaches, which straighten these trajectories. With that, you get less diversity, but you get much faster inference. And with that, you see that the two are complementary to another. One gives you diversity, but takes quite a bit. The other is fast, but less diversity. So we've been taking a standard diffusion model out of the box without any distillation, any of these costly processes, and then take the output of this model, or not the output, in the latent space that we had in Stable Diffusion, and add a flow matching approach, which takes the low res and matches that in an optimal transport fashion, so as directly as possible, taking straight trajectories over to the high-res output latents, which then our autoencoder that I mentioned before and can turn into pixels. And that turns out to be a super effective approach without requiring costly distillation. So one of my key takes there is that intelligence at the end of the day arrives when you have to solve complicated problems with finite resources. That's what our brains are actually doing. We use the same brains as our ancestors used, and they just had sticks and stones, and we're dealing with complicated machines there. And this finite hardware there required us to come up with intelligent ways of actually dealing with problems. And I guess as a research lab, without infinite compute, you also need to go for these intelligent solutions there, rather than taking what you have and just put that on steroids by investing more into GPUs. And I guess that I see from a research perspective as something very appealing, and that I see also from the application side for users as something that is appealing. And I guess Stable Diffusion to a certain point shows that there is something to this theory that I just outlined.
I wanted to ask about world models, and a lot of what you've been talking about sounds like world models where you're getting input directly from images, for example, or presumably video that seems to be coming very quickly, as opposed to through the filter of language. Greater grounding in reality than the at least the original LLMs. It's amazing. We can talk about the original LLMs. It's only a few years now, but that were purely synthesizing the knowledge that's contained in language. Is it related, your research, to world models?
I find constructivism very appealing. Constructivism in the sense of Piaget, our brains creating a mental model of the outside world and being kind of this active scientist that actively explore the world out there, doing tiny little experiments and then making predictions, essentially in the sense of predictive coding. And then we probe and see, does that work? Does my prediction about the next frame in a video sequence work out or not? Then I need to adjust things and so on. And that I find very appealing. And I guess we need to be humble there. And I guess that is also one of the lessons that I've learned from 2 decades or whatever of vision research there. These problems are super challenging that we're dealing with. Making sense of the world by just observing a bunch of pixels is a challenging problem. It is every now and then that you're granted this opportunity to move on a tiny mountaintop and see what's before you, but you see the next ridge of mountains and you cannot see behind that. And with that comes that, if you look back what GANs, for instance, generative adversarial networks, were doing, that looks like these humble models and almost not doing anything compared to what we're having. Now, if you look 1 year back, like what we did in Stable Diffusion looks like tiny baby steps compared to the nice results that we're having these days. And the same will probably be true in a year and 2 from now with video and the like. But saying that we will have a full up model of our world, which essentially I was alluding to visual understanding in my talk there as well. And this is a goal, but we will only achieve that in part. And I would be careful to sort of go too far there, because that's one lesson that we've learned from development in neural networks and AI winters and so on, that we came up with these promises there. Hey, I have 1 neuron, you give me a few billion more and I will eventually have the brain. And then we figure out the structure is probably a little bit more complicated. It's not just like linearly adding up there. And the same holds true for many of the developments that we're having these days. So I'm by no means concerned that I will run out of research challenges in the upcoming years.
The title of your talk was something like The Fallacy of Scaling, or the big companies that are in this are going to continue to scale because the scaling laws are holding. So far, they appear to, but
I would say, like in 2007, what we call Dennard scaling has ended. So this integration that Richard Feynman, like 6 decades ago, had predicted, that you can make transistors smaller and smaller. And with that, they need less power and their frequency goes up and so on. And that has come to a certain end. The integration, I guess, when your audience can see that the processors that they're buying these days don't have many more sort of their frequency than they had 5 years ago or whatever else, compared to what we had 10, 20 years ago, where every year you were seeing an increase there. Then we had parallelization with GPUs and so on, and that's what deep learning has benefited from quite a bit. But this is by no means as quickly ramping up the GPUs in their performance compared to what the demand side, our models in AI, actually would be able to actually take in. And with that come limitations in the scaling. It's like the canary bird and when you go under the ground in a coal mine or whatever else. It's first the smaller companies, research labs and so on noticing. And these days, it's even the big companies that are noticing that. Like if you look at GPT-4, after first being released, got linearly better. But there are parts where it's even gotten worse. Even with large donations or contributions, I should say, by a big company, that wasn't infinite amount of money, and that wasn't infinite compute that they had. And we see that even with these enormous amounts of money, you cannot just throw it at it and it's constantly getting better. There are trade-offs involved in that development. And with even that big companies, with that much resources noting it, the writing is on the wall that just scaling up, we will see scaling up, and this is important, don't get me wrong on that, but this is not the only way to go about. We will see classical engineering, scaling things up happening, but I think the scaling up is the single most consistent factor if you go back half a century or whatever else, which correlates with a lot of developments there. But with that, it overshadows important technological sort of breakthroughs and paradigm shifts that we had at the same time. It's not that the GPUs that we're having these days are just electron tubes or relays from 100 years ago on steroids, made smaller and faster. We had developments like the transistor, like the integrated circuit afterwards, and only they were able to actually get us there. I guess the same thing that we're seeing in AI as well. We have not just the MLPs that we had decades ago, and the same way we will have different architectures as well. So taking something that was there and just scaling up just gets you a certain way. We will have these paradigm shifts, hopefully, in the very near future as well, because there are challenging problems, which I believe we cannot only solve by means of scaling.
That's it for this episode. I want to thank Bjorn for his time. If you want to learn more about today's conversation, you can find a transcript of the episode on our website, EYE-ON.AI. And remember, the singularity may not be near, but AI is changing our world. So pay attention.